I'll be right back. I am live. Here we are. Goodness gracious me. It has been a few days before I have been able to go live and do this exact thing where I do my normal, usual live. It is still the iPad for this live because I'm still working on getting myself a phone for the lives. There's a weird spot on the screen. Okay, great. Here we are. Welcome to the live. Welcome, welcome, welcome all. Welcome one, welcome all. Good morning, Asia. Very early good morning to Europe, Africa. Good evening, North America, South America, all of the continents, Antarctica. Everybody, thank you so much for joining. If you're joining, thank you so much for watching. If you're seeing this as a video upload later on, how is everybody? I've missed going live and I've missed seeing everyone here. So let me know. I'll share the live. I'm looking at my laptop over here where I will share the live. I will look at the chat because this is still the iPad live. The chat messages are a little bit hard to read on the iPad, so I've been using the laptop to read all the messages from you guys. So thank you once again so very much for being here, for joining. I'm still adjusting the distances and stuff too. Today, for our science part, so as you know, we cover physics, astronomy, astrophysics, cosmology, along with kitty cats, hanging out, catching up with everybody, and all of that on the lives in this channel. If you go to the live tab on my channel, you will see many such other live streams that I also encourage you to catch up, especially if you're new, because we have a lot of topics posted already. Today, for the physics part, we're going to do trans-Neptunian objects. More strictly, it's actually astronomy, but that's what we're going to cover today. So I'm quite excited to see everybody and say hi to everyone really soon here. Thank you once again. Welcome. Welcome to the live. Hello, hello, hello. Hello, hello, hello. That was my beginning spiel. Now I will share the live. Hello. Hello, hello. Good evening. Ooh, so I was gonna say, so we covered the live. Hi Swartz, hi Haru. If you give me your number, I'll sub. Thank you. You're so beautiful. Thank you. Zen Zen, hello. Sorry. Excuse me, I had to burp. What's your phone number? 1-800. I don't know, NGC7252. Hi, love, good morning. Hi, Harry. NGC7252, I believe, is the name of a galaxy that we have spoken about in with regard to galaxy mergers. So that's what came to mind when you asked phone number. Hello! Hello, everybody. Welcome to the live. What's your name? You can see my username is Oindry B, like Queen Bee, but Oindry B, and then the channel is Baji the Handsome Cat. Her number is 91. Oh my gosh, don't say that. I don't want any more emergencies this week. Let's just put it that way. I was actually in the ER earlier a few days ago, and not wanting to do that again. And it was during a snowstorm as well. Quite the adventure I've had recently. I'm sorry. Thank you. Zen Zen, hello. Harry Green, hello. Swartz, hello. Carrie, hello. Manoj, hello. Swartz, hello. Mr. Ayub, hello. Are you Indian? Yes, indeed. Yes, sir. Yes, ma'am. Originally, are you married? I am not, but thank you, I guess, for asking. That is Oliver. You need to get married. Is it a necessity? I wasn't aware. I'm from Nigeria. Welcome to Nigeria. Welcome, Africa. Welcome, welcome, welcome. You from India. Yes. Haru says that. You from India. Zen Zen says hi. Hello. Hello, hello, hello. I'm quite enjoying saying hi to everybody, actually. Haru says, I can't believe you need babies. I actually already have babies. They're feline, but babies are definitely part of the household here. Mike, my name is Mike Oxlong. Hello, Mike Oxlong. Welcome everybody to the live. Thank you for being here. Thank you, thank you, thank you. Can I be with you? You can definitely be on this live. And please do, can we get 20 likes? Can you please like the live? That would be amazing. You're so beautiful. How can you be? What job you do? Oh, academic grants. What job? What's your name? Thank you everybody for coming to the live. Can you please like the live? Thank you for liking. Can you shout my son? His name is Ben Dover. Thank you for liking the live. Thank you. What kind of physics are we talking about? Classical, thermodynamics, quantum. Today we're going to talk about astronomy actually. Math is boring. It's always X and Y. Never you and I. Oh my gosh. Well, that's quite a poem. Goodness. How old are you? Well, how old are you, Mr. Ayub? Thank you for liking the live. Thank you so much. Thank you so much. Thank you so much. Thank you so much. Can I talk business with you? You can. You can talk about anything you want. 34. I wish to come to India to see you, but I don't have the flight's fare. Well, I'm not in India. I'm in Boston, in North America. What about astronomy, says Chief Kitten Mittens. We will talk about trans-Neptunian objects in a little bit, once I'm done saying hi to everybody and reading this very interesting comments. I don't mix love and money. Well, you should definitely only talk about business then. That would be amazing. No paper, no pen, but you still draw my attention. 3x plus 7 is equal to 307. What is x? 100? Nice. I grew up in Boston, but it got to be expensive. I know you know CPR. The live. That would be amazing if you could like the live. I have to clip that. I know you know CPR because you took my breath away. Oh my gosh. Well, thank you, Harv. That is the funniest thing that I've read today. Yeah. You know, today has tended to be a bit of a serious day. I was reflecting on all kinds of things, and mainly I just wanted to feel better and feel good and come to the live, and I was thinking about all the work I want to do, and I hadn't really had a laugh today. Shout my uncle, it's his birthday. His name is Ihava. Okay. Can you, hi Ihava, shout out to you, the uncle. Thank you for watching. Thank you for being here. Welcome to the live. Can you please like the live? Can you put people in power to get nuclear thermal rockets on track? Thank you, everybody. Thank you so much. Where are my usuals? Where are my regular peoples? Reese, Ben, Doro, where are you? Why pick up lines? I rather pick you. Oh my gosh. Goodness gracious me. So yeah, because I've been kind of recovering and I was thinking about all the work I want to do and all the things I want to accomplish today, including this live, I was like a little bit serious. The energy was a little serious all of today. But thank you for the very funny comments. My real name is Nick Hare. Nick Hare. I like it. It's a good name. Smile. Well, you don't have to tell me to smile. Ooh, I've completely forgot to share the live. Thank you for being here and thank you for sharing your thoughts, and thank you so much for liking the live. That would be amazing. Thank you. Come one, come all, come and join the live. Thank you so much. Yay! Yay, yay, yay. Okay, I paused my own live over here. Hello! Hello, hello, hello. Hello, my lovely friends. Hello, welcome to the live. Thank you for liking. Please do like the live. Can we get 10 likes? Can we get 10 likes? Can we? Suraj hua madham. Sometimes I start singing. Do you have a map? Because I got lost here. चांद जलने लगा आसमान ये हाय क्यों पिघलने लगा मैं चलती रही ज़मीं चलने लगी. If I were to rearrange the alphabet, I would put you and I together. Goodness. Lo. I will say that is quite funny. Do you go to the gym? I do. Why do you ask? I named my dog Ben N. Sidme. Side Ben N. Okay. Hello, welcome. What exercises do you do? Why do you ask? Why do you ask? I do swimming mainly. My dog name is Ben 10. I do swimming for my mental health. Could we please get 10 likes? Can we get 10 likes? 10 likes, 10 likes, 10 likes. Suraj hua madham. Ooh, let me sing an English song. Imagine all the people living life in peace. Woohoo! I don't think that's quite the wordings. Usually I kind of forget the lyrics and I remember the tune. Beautiful voice, thank you. My cat's name is Chutki. Aww. You may say I'm a dreamer, but I'm not the only one. Hope someday you'll join us. On this life, we'll live as one. Can we get 10 likes, please, before I start the trans-Neptunian objects? 10 likes, please, 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 please. Do you have any injuries? Why do you ask? I hope not. If the world was ending, I want to be with you. Aww. Well, thank you for your support, everybody. We will get started with our topic today. I'm gonna name my daughter my Dixie. Dolakpur Laddu. Are you naming a type of dessert? Oh, thank you for liking the live. You may say I'm a dreamer, but I'm not the only one. Hope someday you'll join us, and the world will live as one. A trans-Neptunian object, or TNO, can be broadly defined as any object that is orbiting our sun, our very own solar sun system sun, at an orbit larger than the orbit of Neptune, which is at around 30 astronomical units. So you know how the Earth is 1 astronomical units from the sun? Neptune is quite a bit farther away. We've also talked about all of the planets in our solar system, just FYI. If you go to the live tab on my channel, you will find many such lives in the past where we've covered every planet in quite a bit of detail from this book right here, Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson, our favorite authors of all time. And we also reference some other books as well on this channel, but I think I should put this book in my channel description because we've been using it so very much. Thank you so much to the authors. Thank you so much to astronomy. Thank you so much to the history of science, which has allowed astronomy to evolve and flourish to the point where we can now do amazing observations into this universe, this galaxy and beyond. In fact, just over 100 years ago is when we started to discover many more galaxies than our own, and Hubble is the one who helped us with that. We have also spent time talking about various galaxies and various galaxy classifications, especially based on their shape, which gives us spiral galaxies, elliptical galaxies, and irregular galaxies. We've also talked about active galaxies in recent lives. So if you're interested in any of that, you should definitely check out those particular live episodes. Hopefully I've named them something that is kind of indicative of what is covered in the live, but sometimes indeed the live streams kind of evolve on their own and have mind of their own, depending on the audience and the type of conversations and discussions that we're having. Today I'm determined to talk at least a little bit about trans-Neptunian objects. We have covered all of the planets, of course, the rocky planets, Mercury, Venus, Earth, and Mars that are closest to the sun, and also we have covered the Jovian planets. These are the Jupiter-like planets, so Jupiter, Saturn, Uranus, and Neptune. These are much bigger. The compositions of them are quite different, and we have covered them in a lot of detail, including their moons. We have talked a lot about the moons of these planets as well. Today, it will be interesting to see what we mean by trans-Neptunian objects and what specific things there are to learn about them. And of course, as you know, some people's favorite planet, Pluto, is actually been demoted to a dwarf planet now, so it's no longer a planet, but a dwarf planet, and that will also appear as a character today on today's live episode. So thank you so much once again for being here. Welcome to the live, and we will now get started. So again, we know, so just to give you some scale, we on Earth are from 1 astronomical units from the sun. So the distance between the Earth and the sun is 1 astronomical units. That distance is basically given that definition. 1 astronomical unit is the definition of that distance between Earth and sun. Jupiter is at around 5.2 astronomical units from the sun. It's the biggest, most massive planet in the solar system, and it's at sort of the middle of the solar system. So it's 5 times farther away than us from the sun. And then Neptune is at a little over 30 astronomical units from the sun. So what we mean by trans-Neptunian objects is the solar system has even more sort of objects in it that we will now take a look at. And these are going to be orbiting the sun at an orbit that is much larger than even the orbit of Neptune, which is a pretty big orbit. It's at 30 astronomical units, so you can imagine that's quite far away. So that's what we'll take a look at today. Are you Patrick? Because I can be your star. Patrick. Not sure what that means. Thank you once again, everybody, for being here. We will now continue the trans-Neptunian objects topic. So one more time, a trans-Neptunian object, or TNO, can be broadly defined as any object orbiting the Sun on an orbit larger than the orbit of Neptune, which is at 30 astronomical units from the Sun. Thank you for liking the live, by the way. Thank you so much. Really appreciate it if you could like the live. Could we get 20 likes? Thank you. Ever since the discovery of Neptune in 1846, so as you know, as we've kind of gone over in the past as well, the discovery of all the different planets did not happen all at the same time. As astronomy has kind of evolved and we've made strides in observation, we have come across more and more things. So Neptune was discovered in 1846. Astronomers since then have looked for trans-Neptunian. So once you find Neptune at a distance of 30 astronomical units from the Sun, which is so far away than, for example, where we are from the Sun, of course, you'd be curious to know, well, are there more? In the early 20th century, the astronomer Percival Lowell instituted a search for Planet X. So kind of like SpaceX, but in this case, Planet X, using the facilities of his private observatory in Flagstaff, Arizona. It was realized that a planet farther away than Neptune would be faint and would not necessarily be resolved in angular size. The basic methodology used was to take photographs of areas near the ecliptic that were close to opposition. By comparing photographs of the same area taken several nights apart, so photographs of the same area in the sky taken several nights apart, objects in motion relative to the background stars, because of course there's also the background of all the stars in the sky. So once again, by comparing photographs of the same area in the night sky, taken several nights apart, objects in motion relative to the background stars can easily be detected. The Earth's average orbital speed is 2 pi astronomical units per year. Since v is proportional to r to the -1/2 for Keplerian motion, so this is coming from Kepler's laws, an object on a nearly circular orbit with semi-major axis A will have an orbital speed given by around 2 pi astronomical units per year times 1 astronomical unit over A all to the 1/2. So that's a little bit of math for you. We will skip some of this, which tells you more about this orbital speed and whatnot, and go to the next part, which is that objects beyond Neptune with semi-major axis of 30.1 astronomical units, that's where Neptune is, have an apparent angular speed, omega, of less than 1.6, so less than 1.6 arc minute per day at opposition, and can easily be distinguished from asteroids at around 3 astronomical units. So remember, we have to kind of see, like, not only do we have to see the objects and see kind of what they're doing, but also we have to be able to tell them apart from asteroids and some other random things in the solar system. So that's why we have to consider this. So again, objects beyond Neptune with the semi-major axis A of 30.1 astronomical units and more have an apparent angular speed of less than 1.6 arc minutes per day at opposition and can easily be distinguished from asteroids at A equal to 3 astronomical units. So thank goodness the asteroid belt is obviously closer, which have the much faster retrograde motion of around 12 arc minutes per day. So compared to 12 arc minutes per day, we have 1.6 arc minutes per day for the objects beyond Neptune. In the year 1930, so much more recent because Neptune was discovered in 1846, so we have from 1846 to 1930 to do this work. A young astronomer in the year 1930 named Clyde Tombaugh compared photographs of a small region of Taurus that had been taken on January 23 and January 29 of that year. So remember, astrology is also based on a lot of these constellations and things like that. I'm not a hugely knowledgeable about astronomy, but if you, astrology, I do know astronomy, but astrology I know less of. But if you're a Taurus, put that in the chat. Maybe you are. If your sun sign is a Taurus, then here we go. We're talking about Taurus. So basically, young astronomer Clyde compared photographs of a small region of Taurus that had been taken on January 23 and January 29 of that year, so in 1930. He found one faint, unresolved point of light that had moved by around 9 arc minutes between one photograph and the next. So if you're taking a lot of photographs, you really have to kind of see what are the differences, and it could be very small differences, and if things have moved even a little bit, that could, be something important. So he found one faint, unresolved point of light that had moved by around 9 arc minutes between one photograph and the next. Further observations revealed that the newly discovered object was on an orbit with or the semi-major axis of 39.5 astronomical units. So that's not too far from Neptune, because Neptune is at 30.1 astronomical units. This is 39.5 astronomical units, a bit farther away. And the eccentricity was E equal to 0.249. So remember, these orbits may have various different eccentricities, and that's why we're mentioning that. And the inclination was 17 degrees. The object was given the name, guess what? Some people's favorite planet, not quite yet, or not quite a planet anymore. The object was given the name Pluto, after the Roman god of the underworld. So god of the underworld, Pluto, right here, right now. We're getting into the discovery of Pluto. Some people's dogs are named Pluto as well. So that's what we are talking about. The object was given the name Pluto after the Roman god of the underworld and was declared to be the 9th planet. So people thought that we have discovered the 9th planet because, of course, when you start discovering more and more planets, you've already discovered Neptune in 1846, now you're seeing one more thing, people will think that, oh, there are more planets in the solar system, and we're chancing upon that. It was an unusual planet, though. So as you know, just for the record, Pluto is no longer considered a planet, it's considered a dwarf planet, but here's the discovery of it. It was an unusual planet given its high orbital eccentricity. So the orbital eccentricity and inclination of Pluto does make it quite different than all of the other 8 planets, or, well, all of the other, all of the planets. It's much more in line with, as we know, the category of a dwarf planet at this point. But at that point too, they thought, okay, maybe we discovered the 9th planet. They hadn't quite come to the conclusion that where we are now, because things kind of progress over time, right? Only later on we classified this as a dwarf planet, but when it was first discovered, they thought, well, this is maybe the 9th planet, and sort of unusual given its very high orbital eccentricity and inclination. But it really didn't fit into any other category in use at the time. So we didn't have these other categories at that time, so we just call it the 9th planet. It lay far outside the asteroid belt, and it was significantly larger than Ceres, the biggest of the asteroids. So we can't really, we were like, it's not really an asteroid because it's quite a lot bigger, significantly larger than Ceres, which, by the way, is Ceres. Hopefully I'm saying that right. If not, feel free to correct me. Pluto was significantly larger than an asteroid. So you know, we can't really call it an asteroid at that point. Modern measurements of the radius of Pluto, at this point we know it is 1160 kilometers. So again, figuring out the radius of something that far away is not a trivial matter, but at this point we know it's around 11,000, 1100, sorry about that, 1160 kilometers, so 1,160 kilometers, which is more than twice the radius of Ceres. So Ceres as an asteroid is quite a bit smaller than Pluto, which we thought at that point was the 9th planet discovery. Really, it's a dwarf planet as we know now. For nearly half a century, Pluto was the only trans-Neptunian object known. So Pluto, even though it may have been demoted from a planet, remember it has quite a bit of significance because trans-Neptunian objects in general were not super known at that time. So when you're in the 1930s and 40s, like discovering Pluto is quite a big deal. So if you're a fan of Pluto, here you go. It has quite a bit of significance, okay? So for nearly half a century, 50 years, Pluto was the only trans-Neptunian object known. Then in 1979, Pluto was discovered to have a satellite. So not only is it a trans-Neptunian object that we have found, another whole object that we have found, we thought it was the ninth planet, but now it even has a moon. So it was given the name Charon. Charon, Charon, however you want to say that word. Charon is the spelling. This is a satellite of Pluto that was discovered in 1979. So, because the distances that we're talking about here is quite large, Pluto is a trans-Neptunian object quite a bit farther away from us. Discovering it and then discovering its moon is not trivial, but it was very important when we did discover these things. So again, now we have Charon, which is named after the ferryman who transported dead souls into the realm of Pluto. So since Pluto is named after the god of the underworld, its moon Charon was given the name this name because named after this ferryman who transported dead souls into the realm of the underworld, I suppose. I'll show you a picture of Pluto and Charon in a little bit as imaged by the Hubble Space Telescope. The mass of Charon, so you might be curious, how does Charon compare with the mass of Pluto? So the mass of Charon is 1/8 the mass of Pluto, so that is 1/8 the mass of Pluto. So that's quite a big ratio, actually. So that is the most massive satellite relative to its parent body. So being 1/8 of its planet body size, as in mass, is actually quite interesting. So Charon is 1/8 the mass of Pluto. That is the most massive satellite relative to its parent body in our solar system. So quite interesting, very, very interesting. So for comparison, the moon is 1/81 the mass of the Earth. So so the 1/8 is crazy, right? The moon is 1/81 the mass of the Earth. Charon is 1/8 the mass of Pluto. So it's almost like they're almost like a binary, right? Which is fine. That's fine. Pluto and Charon are separated by a distance of only 20,000 kilometers. Wow. That's very small. Pluto and Charon are separated by a distance of only 20,000 kilometers and orbit their center of mass with a period of 6.4 days. So as you know, two bodies will kind of orbit around the combined center of mass. And so Pluto and Charon, which are only 20,000 kilometers apart from each other, will orbit their combined center of mass at a period of 6.4 days. And in this case, Charon is only 1/8 by only I mean it's 1/8 the mass of Pluto, which is quite a bit of mass compared to its parent planet body. So the center of mass is not super close to Pluto. It's closer to Pluto, but somewhere in there in the middle. Pluto and Charon both show brightness variations with a period of 6.4 days. That is, both Pluto and Charon have been tidally braked until they are in synchronous radiation. Oh my gosh! That's amazing. That's amazing. Pluto and Charon have been tidally braked. BRAKED, braked. So kind of like slowed until they are in synchronous rotation, because their masses are not so different, and the distance between them also not very, very, very big. So the discovery of 2 additional small satellites of Pluto in the year 2005. So as recent as 2005, I guess it's not very recent to the younger people here, but as recent as 2005, we have 2 additional small satellites of Pluto, namely Nix and Hydra. Very cute names, Nix, N-I-X, Nix, and Hydra, H-Y-D-R-A. Enabled more accurate estimates. So by the way, once you discover more satellites of something, that actually helps you to get better estimates of the masses of things, such as the mass of Pluto. So this enabled the discovery of the 2 additional satellites, enabled more accurate estimates of the mass and thus the density of Pluto and Charon. The mean density of Pluto is 2,000 kilograms per meter cubed. So remember we had talked about the sort of the densities of all the planets. Because Pluto is no longer considered one of the planets, it's considered a dwarf planet. It didn't really figure in that same table, but we had looked at all the densities if you kind of go back to that live where we talked about the planets. The mean density of Pluto is 2,000 kilograms per meter cubed. That is meter cubed. So it's a density, meaning it's a mass over a volume. So the mass is in kilograms, the volume is in meters cubed or cubic meter. I had to think about that. The mean density of Pluto is 2,000 kilograms per meter cubed. That is actually less dense than our moon, by the way. So the mean density of Pluto is 2,000 kilograms per meter cubed, consistent with its being 70% rock and 30% ice. The lower density of Charon, which is 1,700 kilograms per meter cubed, indicates that it is probably half rock and half ice. Again, we have to spend time and resources on Charon if we want to figure out more details about it, but this is what we estimate at this time. Reese, how are you? I'm better, but I've been sick. Thank you so much for coming to the live. Although the surfaces of Pluto and Charon have been observed with the Hubble Space Telescope, that is, by the way, getting time on Hubble Space Telescope is, something that a lot of astronomers, want to do. If you want to get a PhD in astronomy, you might have to request time on the telescope, that is. The limits, so although the surfaces of Pluto and Charon have been observed with the Hubble, the limits on angular resolution mean that features smaller than a few hundred kilometers across cannot be seen. So even the Hubble will struggle to see things with a lot of resolution when they're so far away. Even at low resolution, however, it is apparent that Pluto has variations in its albedo. So now remember, what is albedo? The darkest, so albedo has something to do with reflectivity, okay? So the darkest regions, remember we talked about that with all the other, with all the planets as well, and some of the moons as well, and tells us something about the atmosphere, the surface, things like that. The darkest regions have albedo of less than 0.5, while the brightest regions have albedo of 0.66. This is surprisingly bright compared to other icy bodies in the outer solar system. Icy bodies darken over time because, among other causes, long exposure to solar UV radiation tends to darken methane ice. So now remember that when we say icy bodies in our solar system, we don't just mean ice as in water ice. It can be some other compounds ice form. So methane is one of them. So methane ice can be kind of darkened over time from exposure to solar UV radiation. One second, sorry, I had to mute that. Icy bodies darken over time because, among other causes, long exposure to solar UV radiation tends to darken methane ice. The explanation for the anomalous, so we expect that methane ice will darken, but there's this anomaly of the brightness of Pluto, which seems to be kind of higher. So the explanation for the anomalous brightness of Pluto lies in its eccentric orbit. Because the orbit is so eccentric, right? It's a very strange orbit compared to the planets, to the other planets. And I keep saying other planets because somewhere in our brain, Pluto is sort of the 9th planet. At this point, we know it's a dwarf planet, but there we go. The explanation for the anomalous brightness of Pluto lies in its eccentric orbit. The surface temperature of Pluto at perihelion, so peri, again, remember, means near. So perihelion meaning when it's closest to the sun. It has a temperature, the perihelion distance is 29.6 astronomical units, and the temperature there is 51 kelvins. So very cold. I mean, 51 kelvins is quite cold, for example, compared to us on Earth. But remember, we're talking trans-Neptunian objects, which is very far from the sun. So that is considerably warmer. The perihelion temperature, that is considerably warmer. Even though 51 kelvins sounds quite cold, but it's considerably warmer than aphelion temperature of 40 kelvins. So at aphelion, it's 40 kelvins is the surface temperature on Pluto. At perihelion, when it's closer to the sun, it's 51 kelvins. Okay. Goodness. So once again, the surface temperatures of Pluto are 40 kelvins at perihelion, or sorry, aphelion, ap meaning away, and 51 kelvins at perihelion, peri meaning closer. At perihelion, some of the atmosphere sublimes. So again, as you can imagine, as Pluto is going through its orbit, of course, its sort of life is kind of different as it's at different distances from the sun, and it's a very eccentric orbit. So quite a bit of a difference between Pluto's perihelion versus Pluto's aphelion, right? So basically at perihelion, some of the atmosphere will sublime. It's too hot, right? Sublimation, remember, is a phase transition of certain materials. Basically goes from one phase to the gaseous phase. It could be from solid or liquid to a gaseous phase, giving Pluto a temporary methane atmosphere. So remember, we talked about how sometimes certain planets, or even, well, I want to say certain planets, basically will have a temporary atmosphere based on their distance from the sun and based on what activity is sort of getting, what activity they're being exposed to. So in this case, if methane kind of sublimes, it gives Pluto a temporary atmosphere when it is at perihelion. As Pluto moves farther away from the sun, however, the atmosphere freezes out again. So it becomes ice again, ice methane instead of sublimation phase methane. And that might be why it did not darken. You know, we talked about the brightness of Pluto, so really cool. This puts a fresh, highly reflective layer of methane snow on Pluto's surface once per orbit, every 248 years only. So because Pluto goes around the sun every 248 years, and that type of sublimation and ice snow, it snows methane on Pluto. When it's closer to the sun, you get that fresh, highly reflective layer of methane snow on Pluto, giving it the look that it gets. Thank you so much for joining the live. Can you please like the live? Can you like the live? Hi, Stephen. Hi, Reese. Let me say hi to everybody really quickly. So, hi, Haru. Hi, Reese. Hi, Stephen. Thank you. Thank you so much. So, Pluto, so by the way, isn't that cool that Pluto passed through perihelion in the year 1989? Because of the high eccentricity of Pluto's orbit, Pluto was actually closer to the sun than Neptune was during the period 1979 to 1999. So Pluto has a highly eccentric orbit, as in its distance from the sun is very different when it's at perihelion versus when it's at aphelion. And because it was at perihelion in the year 1989, wow, goodness, close to when I was born, Pluto was actually closer to the sun than Neptune was during the period 1979 to 1999. However, because of the high inclination of Pluto's orbit, the paths of Pluto and Neptune never intersect. When Pluto is at the same distance from the Sun as Neptune, it is several astronomical units away from the plane of Neptune's orbit. In addition, Neptune, with orbital period of 163.7 years, so Neptune's orbital period is again 163.7 years, and Pluto orbital period being 248 years, are nearly in a 3 to the 2, so 3 to 2 ratio orbital resonance. The synodic synodic period of Pluto as seen from Neptune is 481.7 years. Wow. Which is close to 3 orbits of Neptune and 2 orbits of Pluto. This means that as seen from Neptune, so if you're on Neptune, Pluto will be at opposition at approximately the same place in its orbit each time. At present, this happens to occur when Pluto is near aphelion. At aphelion, Pluto's distance from the Sun is 49.2 astronomical units, which means it is nearly 20 astronomical units from Neptune. Wow. Yeah, I've been ill. I was in the ER a couple days ago. Not couple. I was in the ER on Saturday. I had to go to the ER during a snowstorm. Ugh. It was awful. Actually, my stomach hurts right now. Aww. I did, Steven. You and me both. Oh my gosh. Can you please like the live? I did have to do the year. It was not good. That's why I missed the live. I missed going live on the weekend. Oh gosh. Ugh. Okay, give me 1 second. Thank you. Okay, next we will talk about the Kuiper Belt. Kuiper. Oh gosh, I'm so sorry. But yesterday I did go live actually. Last night I did go live around 1 in the morning. It wasn't a face live because I was still feeling so yucky. But I did go live last night. I'm so sorry you waited. Aww. One second, sorry. We will cover the Kuiper Belt in just a second. You didn't see it? Yeah, I know. You guys didn't see it. I think it was too late. Like people were. It was you know what I mean? Like it wasn't a very good time. Oh, that was you. I waited up all night last night for your live. Oh, I thought that was Steven. I was still working at 1. It's pronounced Kuiper. Is it Kuiper? Sorry. Thank you so much. Kuiper. Thank you. Oh wow, that's cool. Okay. I even sang a little bit towards the beginning today, but now I'm gonna cover the Kuiper Belt. Imagine all the people Sunday night, Elon Musk launched a bunch of satellites that were visible all over the world. It was so cool too. We were at a campfire birthday thing in the woods. There was a little girl there and she was petrified. Really? Harper! But yeah, sorry you missed my live last night and I missed going live for a few days. Saturday, Sunday, I was so sick. I'm still kind of sick actually, but I'm recovering. But yeah, missed you guys. Harper! Here we are, Harper. Thank you for joining. Thank you for joining, everybody. Thank you. Batman. As early as the mid-20th century. So now we're going to talk about the Kuiper Belt, which Reese told me it's called Kuiper, Kuiper. And I don't know if he knows English though, so, you know, we'll see. You tell me if that's wrong. As early as the mid-20th century, it was predicted that the region beyond Neptune should contain not just one or two ice covered, not just one or two ice-covered bodies, but a very large number. In 1951, Gerard Kuiper pointed out that large numbers of icy bodies condensed in the cold outer parts of the pre-solar nebula. So remember, we all come from a gas cloud or a nebula, a pre-solar nebula, meaning before the sun was a thing and before the planets were a thing. So in 1951, this guy pointed out that large numbers of icy bodies condensed in the cold outer parts of the pre-solar nebula. Although many of those bodies were scattered by the gravitational influence of Neptune and the other Jovian planets, Kuiper predicted that some of the icy bodies should still remain in a circular ring beyond the orbits of Neptune and Pluto. As a consequence, the region close to the ecliptic plane at distances from around 30 astronomical units to 50 astronomical units from the sun is called the Kuiper Belt. Yay! Thank you for liking the live. Can we get 20 likes? Thank you, thank you, thank you. Can we get 20 likes? Thank you, thank you, thank you. Small bodies beyond the orbit of Neptune are faint and thus difficult to detect. So yeah, if we can try to image these things, but they're so far, it's going to be faint. The first trans-Neptunian object other than Pluto and Charon was detected in 1992. So as recent as 92. The object named 1992 QB1 is on an orbit with a semi-major axis of 43.7 astronomical units, an eccentricity of 0.065, and an inclination of 2.2 degrees. Thank you for liking. Thereafter, TNOs, or trans-Neptunian objects, were discovered at an increasing rate. Over 1,000 TNOs were detected in the 15 years that followed the discovery of 1992 QB1. So remember, for the longest time, Pluto was the 9th planet, but then now we've discovered a lot of these trans-Neptunian objects. The orbital parameters of the known trans-Neptunian objects are going to be plotted here. See, we will look at this in just a second. The upper panel shows orbital inclination I as a function of semi-major axis A. The lower panel shows orbital eccentricity E as a function of A. We will look at this. Uranus is the large dot. We will see this dot, and a semi-major axis of 19.2 astronomical units and a low inclination and eccentricity. Neptune is the large dot at 30 astronomical units for the semi-major axis and low inclination and eccentricity as well. We also have a number of objects with orbits smaller than that of Neptune in this figure. These objects, which lie outside the orbit of Jupiter but inside that of Neptune. So there is a name for objects that lie outside the orbit of Jupiter, so outside of 5.2 astronomical units, but inside that of Neptune. And these are called centaurs. It's kind of like Harry Potter, centaurs. This is because the first such object discovered was given the name Chiron. Oh, I think Chiron is pretty important in astrology as well. So the first such object discovered was named Chiron, Chiron, after the most famous of the mythological centaurs. Most of the trans-Neptunian objects have a semi-major axis that place them in a narrow classic Kuiper Belt, with the semi-major axis basically lying between 35 and 50 astronomical units. Most inclinations are relatively small, with the majority of TNOs having an inclination less than 10 degrees. But this is partly a selection effect. The early searches for trans-Neptunian objects concentrated on the region near the ecliptic. Concentrated on a region near the ecliptic. Eccentricities have a fairly wide range, with E being between 0 and 0.3, but a few have higher eccentricity. Notice that there is a large excess of TNOs with a semi-major axis of 39.5 astronomical units, similar to the semi-major axis of Pluto's orbit, right? Pluto was found at around 39 astronomical units. These objects called Plutinos. So now we have Plutinos, Plutinos. Chiron is spelled Chiron, Chiron. But now we have these Plutinos, little Plutos, after their prototype, are all in a 3-to-2 orbital resonance with the planet Neptune. Remember, that's how Pluto was too. In addition, there is a smaller but still significant excess of TNOs with a semi-major axis of 47.8 astronomical units. So we're kind of just finding all kinds of things that are sort of beyond Jupiter, and also some of them are beyond Neptune. These bodies have sidereal These bodies have sidereal orbital periods of P of around 330 years, so quite a long time, and thus are in a 2-to-1 orbital resonance with Neptune. These objects have been given the name of Tutinos. Tutinos, Twotinos, rhymes with Plutinos, so Tutinos and Plutinos. Interestingly, there are very few low eccentricity TNOs beyond the Tutinos. Most known TNOs with a semi-major axis greater than 48 astronomical units have an E of 0.2, so an eccentricity of, greater than 0.2. In fact, most of these distant TNOs, the distant, trans-Neptunian objects, have a combination of A and E, so semi-major axis and eccentricity, that places their perihelion in the range of 30 to 40 astronomical units. So between 30 and 40 astronomical units, which would be, kind of like Neptune and a bit farther away. So close to the orbit of Neptune. These distant high eccentricity TNOs are called scattered disk objects. The most plausible explanation for their orbits is that they were originally on low eccentricity orbits within the classical Kuiper Belt. So they might have been low eccentricity orbits within the classical Kuiper Belt, but were scattered onto larger high eccentricity orbits by their gravitational encounters with Neptune. So Neptune here is playing a very important role in making some of these high eccentricity orbits have the characteristic that they have. The TNOs have a range of sizes. At present, the largest known TNO is the scattered disk object Eris. So this is Eris, E-R-I-S, Eris, 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 Eris. Someone can tell me how that's pronounced. The radius of Eris is r equal to 1200 kilometers, which means it is a bit larger than Pluto. So we've got Eris now, a little larger than Pluto, because remember Pluto was around 1100 kilometers radius. In fact, I'll give you the exact number. It was 1160 kilometers was Pluto's radius. So now we have found Eris, E-R-I-S, which is the largest known TNO in the scattered disk object, in the scattered disk. The radius is 1200 kilometers, means it's a little bit bigger than Pluto. Eris was discovered in 2005 January. So this is probably sort of where we're gonna be demoting Pluto. So get ready, because Pluto, so far, the 9th planet, is about to get a demotion. So brace yourselves. We have found Eris now in 2005. So Eris was discovered in 2005 January. That month of January was pretty rough from images taken in. So the images were taken in 2003 October, but of course it takes some time, right, to process everything, analyze everything. In addition to being large, so not only was Eris large, it also had a remarkable albedo, as in high albedo of A equal to 0.86. Okay, the reason why it was not discovered until 75 years after the discovery of Pluto is that it is very distant, very distant. Pluto is at around 39.5-ish astronomical units. Eris is represented by the filled square at A equal to 67.7 astronomical units, I of 44.2 degrees, so inclination, and E of 0.44. These are very high. And semi-major axis of A equal to 67.7 astronomical units, goodness gracious, that is very far. At the moment, so this is why we did not find Eris earlier. Even though it's larger and comparable to Pluto, Pluto was a lot closer to us and a lot closer especially to Neptune. At the moment, Eris is close to its aphelion distance, so these things take a long time to orbit the sun. So at this time-ish, Eris is close to its aphelion distance of around 97.5 astronomical units. So far, 97.5 astronomical units. This means that Eris is both very faint and very slow. It's very slowly moving as seen from the Earth, which added to the difficulty of its detection. So very faint and kind of sort of very slow. Because remember, we were talking about the movement of things relative to the background stars and taking a lot of images night after night and sort of like several nights apart. You want to see if something has moved and whatnot to find these other planets, to find the trans-Neptunian objects, as in objects beyond Neptune, which now we have one more of. And very quickly but surely, after this, we will see something shift in our knowledge or understanding about Pluto. So, John Foster, how are you? Harper, good evening. Thank you for joining, Harper. Thank you for joining, Stephen, John Foster, Iggy, hello. So, the third largest known TNO, are you ready? This was about Eris, E-R-I-S, or Eris, however you say that word. Now we will talk about Makemake. Kind of sounds like a sushi, doesn't it? The third largest known trans-Neptunian object, Makemake, is significantly smaller than Eris or Pluto, with a radius of around 750 kilometers. However, its albedo is nearly as large as that of Eris, so reflectivity. And its orbital size is 45.8 astronomical units, which places it significantly closer to us than Eris currently is, because Eris is at aphelion. This means that the flux of Makemake is 6 times that of Eris. Wow. So it's closer, it's very high albedo. In fact, Clyde Tombaugh would have been able to detect it back in the 1930s, were it not for the unfortunate coincidence that Makemake was then passing close to the Milky Way, which provided a bright background against which Makemake could not be detected. So as you know, when we see the night sky, the Milky Way, as we see our own galaxy, is sort of a band across the sky. Not the full spherical, not the full celestial sphere is the Milky Way. When we look at the night sky, most of the things we see are actually other galaxies, or actually other merging galaxies, and then some of them are stars or binary stars. And then, if you're in a very dark spot, you see the Milky Way galaxy, because we're in the Milky Way galaxy, the way we see the Milky Way galaxy is sort of a band across the sky. So imagine if they're trying to, imagine that they're trying to find, some extra, or another trans-Neptunian object. If its background is the Milky Way, well, that's a very bright background. It's going to be harder to tell apart that that little movement or the differences that we look for when we see when we try to see if there is another object or not. Because we want to take images night after night after night, but if Makemake's passage is basically coinciding with the background of the Milky Way, then night after night after night, you will kind of miss it because the background is too bright. Okay? So once again, this is very interesting. So we will read it again. Hi Harper. Harper says, hey John, I'm great. With new horizons out there, they will find many more. Hey Foster. Hi Harper. I was camping years ago in a very light pollution free area and could see the band of the Milky Way galaxy. Yes, I've seen the Milky Way galaxy too from some dark areas. Even if you go to Hawaii or something, you can see it. Or just the beach if it's like really dark there, like some more unknown beach, if you will. It's super cool. Yes. So the third largest known TNO, this is Makemake. It's actually kind of closer, and it has a high reflectivity, high albedo. So it has more flux, and we could have seen it sooner if not for this unlucky coincidence. So we'll read that part again. In fact, Clyde Tombaugh would have been able to detect it in the 1930s were it not for the unfortunate coincidence that Makemake was then passing close to the Milky Way, which provided a bright background against which Makemake could not be detected. What the heck is going on tonight, everyone? Hello, Doro. You'll have to see, so when you have time tomorrow, you should go back to the beginning of the live stream to see what kind of happened. There were some very interesting comments indeed that I think you would find funny. And in fact, you should let the whole video play, and that would be most helpful. Thank you, please, and thank you. Thank you so much. Thank you so much for joining. Hi, John Jones. Hi, Iggy. Hi, John Foster. Hi, Doro. Hi, Reese, and hi, Steven. My regulars. Farther away from the Neptune. Reese, we've been talking about trans-Neptunian objects. Trans-Neptunian. Farther away than Neptune, not Pluto. Wild times here in San Antonio. No worries. Thank you, Reese and Doro. Thank you, everybody. Thank you. I've been sick. That's also what's going on. I've been sick. So I missed the live on Sat and Sun. Very unfortunate for me. The discovery of hundreds of trans-Neptunian objects, one of them larger than Pluto, caused astronomers to ask both the specific question, is Pluto, are you ready for it, a planet? And the more general question, well, what is a planet? So, this is where we experience the demise and indeed the demotion of Pluto as a planet. So listen up. discovery of hundreds. So we spoke about the trans-Neptunian objects, how we started discovering them, and Pluto is one of them. And we thought that Pluto was the 9th planet. But then, after discovering hundreds of trans-Neptunian objects, one of them larger than Pluto, caused astronomers to ask both the specific question, is Pluto a planet? And the more general question, what is a planet? In 2006, the International Astronomical Union, IAU, approved. So, are you guys ready for it? Are you guys ready for this dramatic finding? Thank you. Thank you, everybody, for being here. I can't get distracted. Okay. Thank you, Stephen. Thank you, Stephen. The discovery of hundreds of trans-Neptunian objects, one of them larger than Pluto, called Eris is larger than Pluto, caused astronomers to ask both the specific question, is Pluto a planet? And also the more general question, well, what is a planet? In 2006, the International Astronomical Union, IAU, there's a union for this, approved a definition of the word planet that seemed to the majority of astronomers, I'm sure they fought a lot. So if you think we're about to fight in this chat, you don't know astronomers. I'm sure they fought. To the majority of astronomers who voted on the issue, so they voted on the issue of whether this is a planet or not, or what is a planet rather, the most useful way of defining that word, according to the IAU definition, an object within the solar system is a planet if the following requirements are fulfilled. Can we get 20 likes? It is in orbit around the sun and is not a satellite of another planet. So, number one requirement to be a planet in the solar system. It has to be in orbit around the sun and not a satellite of another planet. Makes sense, not a moon. Number two, it has sufficient mass for its self-gravity to overcome its compressional strength and thus assume a spherical or spheroidal shape in hydrostatic equilibrium. So it has sufficient self-gravity to be spherical, spherical, nice sphere, or spheroidal. Number three, it has cleared its orbital neighborhood. This criterion is sometimes referred to as orbital dominance. It has cleared, so number three requirement to be a planet is that it has cleared its orbital neighborhood. Orbital neighborhood. This criterion is sometimes referred to as orbital dominance. Yes, orbital dominance. Can we please like the live? The 4 terrestrial planets and 4 Jovian planets. So we talked about the 4 terrestrial rocky metallic planets, Mercury, Venus, Earth, and Mars. And the 4 Jovian planets, Jupiter, Saturn, Uranus, and Neptune. 4 plus 4 is 8. There are 8 planets, guys. I'm so sorry. The 4 terrestrial planets and 4 Jovian planets satisfy all these criteria, and so they're labeled planets. Full-on planets. Objects that satisfy the first two criteria but not the last are called dwarf planets. Eris, Pluto, Makemake, Haumea, and Ceres are dwarf planets. Ceres has an orbit similar to that of other asteroids but does not significantly affect their motions. Likewise, Pluto has an orbit similar to that of other Plutinos. Little Plutinos, but does not significantly affect their motions. In fact, all of the Plutinos are dominated by Neptune. Neptune is dominating. Eris has an orbit similar to that of other scattered disk TNOs, but is not sufficiently massive to affect their motions. Oh, God. So that was about trans-Neptunian objects, guys. That was that. That was that. That was that. We just need, oh my God. Well, he comes a bit later, doesn't he? Iggy? Aw? Why is it pseudo-astronomy? What do you mean? Astronomy does evolve. So that was about the trans-Neptunian objects. We can also talk about comets. Aw! Okay, Iggy. Good to know. Random question. If all the planets in the solar system, which planet would you move to if you could? Well, that's a very good question. Reese, you already said. You already told them. Venus. You already told them? I was going to say that. Oh, shut up, Doro. Mr. San Antonio. I remember when Voyager 1 and then Voyager 2 discovered the atmospheres around Titan. Titan and Triton! I love that. It was so cool. Yes! Rudolph the red-nosed reindeer had a very shiny nose. Now I'm happy and I will sing a song. I can't be Mr. San Antonio, I don't live here. You might as well live there now. I have banished you to Texas. Rudolph the red-nosed reindeer. Okay, so I'm going to answer John Foster's question, even though it's been answered already, but I'll tell you exactly why Venus is my favorite. Venus is my favorite. Rudolph the red-nosed reindeer had a very shiny nose. Okay, my favorite planet, and I mean planet, not dwarf planet, is Venus, like Reese has already said. Why is that? Because Venus and Earth are the most similar in size and mass. Both of them are rocky planets, as in they're part of the first four rocky metallic planets with metallic cores. Mercury, Venus, Earth, and Mars, right? Those are the four rocky planets. And Venus is closer to the Earth. So if I had to go somewhere fast, that's not the moon, it would be Venus. Venus is the shiniest, brightest object in the sky after the sun and the moon, of course. Venus is the most like the Earth in terms of size, mass, all that. And I just feel so bad for it because it is too hot to have oceans, liquid water. If Venus had liquid water, then it would have absorbed the carbon dioxide, which makes the atmosphere of Venus, unfortunately, poisonous. But that's how our atmosphere was too. But we are lucky, we're in that Goldilocks zone where we have liquid water and we are blessed by the universe with oceans, which has helped to convert carbon dioxide to rocks by doing chemistry in the ocean and converting carbon dioxide to limestone. If we had done the same thing on Venus, it would have been so similar to Earth and we would have all moved there instead of Mars. Mars is pretty okay, but my favorite would be Venus. I wish Venus's atmosphere was not so poisonous and that it was not so hot there. It is over 700 kelvins on Venus. But that's like, that and its poisonous atmosphere is like its only flaw. You know, its only flaw. And I like a challenge. I like a problem. And so that's why I like Venus. Mars is okay. Mars, the surface of it is very similar to Earth. It's just colder. Bring a jacket. Bring a jacket to Mars. Bring a, I don't know, something to survive Venus. Some way. It's not 800. Oh, you mean in Fahrenheit? I forget what it is in Fahrenheit. It's over 7. It's like 746 Kelvin surface temperature on Venus. Does anyone remember the Apollo-Soyuz mission? The first time ever both the US and the USSR had a joint space mission, the 1970s. I wish Taylor Swift lived on her own. Excuse me? Do not get me started on the moon. Oh wow, 6 pics of the surface of Venus from the Venera landers. I watched a video of someone doing a teardown of the guidance computer and I still don't think... Oh! You wouldn't live on Jupiter to get a good workout. A workout? What do you mean? In what way? In what way? You wouldn't live on Jupiter. We never went. The mass, more gravity, right? Oh, yes. Oh, yes. More, yeah, more gravity. Can we get 20 likes, please? Can we get 20 likes? All right, what song shall I sing today? Rudolph the red-nosed reindeer had a very shiny nose. So in this same chapter where we talked about the trans-Neptunian objects, we also have small bodies in the solar system. We've kind of been talking about that with the trans-Neptunian objects, but we can also talk about asteroids. Asteroids and comets. Let us define asteroids and comets, and then we will do the more in the next live. I don't know this song. Sleeping satellite, sleeping satellite. Dodo, dodo. This live is sponsored by Coco Vita. Not really, but I wish. Da 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 da. Da, 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 da. You don't know Friday by Rebecca Blunt? I think I know Friday. Let me define asteroids. Asteroids were originally discovered as a result of a search for a suspected missing planet. The search was stimulated by what is known as the Titius-Bode rule. Ever since the time of Kepler, astronomers have been searching for numerical relationships along the orbital properties of planets. In the year 1766, quite early, an astronomer named Johann Titius pointed out such a relation. This rule was quoted without proper attribution by the more prominent astronomer Johann Bode, and thus it is frequently referred to as Bode's law. The Titius-Bode rule predicted the existence of planets at A, that is the semi-major axis again, of 2.8 astronomical units, between Mars and Jupiter. So remember, Mars is at, I believe it was at 1.52 astronomical units from the sun. We are at 1 astronomical units from the sun. So Mars is within 2 astronomical units. Between Mars and Jupiter, there's this gap, and that's where we have these things. Between Mars and Jupiter, and at A equal to 19.6 astronomical units beyond Saturn. So we've got these things at 2.8 astronomical units and 19.6 astronomical units. The Titius-Bode rule was regarded as a mildly intriguing bit of numerology until the year 1781. So people kind of, thought it was just like a numerology type of thing, until the year 1781 when the planet Uranus was discovered. So before Uranus was discovered, this wasn't probably getting as much importance. The semi-major axis of Uranus's orbit turned out to be A equal to 19.18 astronomical units. This is close enough to the predicted value of 19.6 astronomical units that astronomers started to take the Titius-Bode rule more seriously. In particular, they started an organized search for a planet with A equal to 2.8 astronomical units in the gap between Mars and Jupiter. So they're thinking, is there really something in that gap? A group of 24 astronomers who call themselves the Celestial Police divided the ecliptic into sectors 15 degrees across. Each astronomer would search his or her assigned region for the missing planet. I guess his in this case. They realized that the planet, since it had not been previously seen, was likely to be very small. However, even if it were not resolved by their telescopes, they could identify it by its motion relative to the background star. So similar to what we were just kind of talking about with the trans-Neptunian objects. Okay, so sort of the motion relative to the background stars. Despite their careful planning, the celestial police were scooped by an astronomer making a serendipitous discovery. Giuseppe Piazzi, director of the Palermo Observatory, was making a highly... Oh, sorry, I thought I heard a voice. Okay. Giuseppe Piazzi, director of the Palermo Observatory, was making a highly precise star chart. To reduce observational error, he observed each star multiple times. In 1801, January, he found that one of his stars had moved from one night to the next. So even though these things sound like they're kind of close to us, actually in the night sky they're kind of far, right? So one of these stars had moved from one night to the next. The newly discovered object which Piazzi named Ceres, so we were just talking about Ceres a bit ago, after the Roman goddess of agriculture, is on an orbit of A equal to 2.77 astronomical units, reasonably close to the Titius-Bode prediction. So it's kind of coming true at this point. Piazzi had no doubt that he had discovered a planet, albeit a small one. Ceres, it turns out, is an approximately spherical body with a radius of around 480 kilometers. So 480 kilometers, so that's smaller than Pluto and everything. About 20% of the radius of Mercury. Things became more interesting, however, when the celestial police went into action and discovered additional objects in the gap between Mars and Jupiter. So we're finding more things, not just the one very tiny planet as in they thought it was, but not really. During the course of 7 years, so this took 7 years, astronomers discovered Pallas, Pallas at 2.77 astronomical units, Juno at 2.67 astronomical units, and Vesta at 2.36 astronomical units. This new class of relatively small objects on closely spaced orbits deserved, it was thought, a new name. So we found some new thing. William Herschel proposed the name Asteroid. Here we are, Asteroid, meaning star-like, asteroid. Wow. Since he could barely resolve them even in his largest telescope, because they're very small. They have also been called minor planets as a reference to their small size compared to the terrestrial and Jovian planets. They're much, much smaller than the planets, whether that's the terrestrial planets or the Jovian planets. So sometimes they're called minor planets, sometimes they're called asteroids or star-like. William Herschel is the one who named them asteroids. There are currently so they looked and they found more. There are currently over 14,000 asteroids whose orbits have been accurately determined and which have therefore been assigned names. Wow. Can we please get 20 likes? Can you please like the live? The list of Roman deities has pretty much been exhausted at this point. So the discoverer of an asteroid is permitted to select any name of 16 characters or fewer that has not yet been used, subject to the constraints of good taste as interpreted by the Committee for Small Body Nomenclature of the International Astronomical Union. So if you want to join this union, maybe you can start naming them as well. The position of the larger asteroids, we will look at that. This, in fact, let me show you right now. Look at that. Here we are. Here we are. Earth-crossing asteroids with semi-major axis of over 1 astronomical units, but with the perihelion inside the Earth's orbit are called Apollo asteroids. Stephen, you probably know about the Apollo asteroids. Yes? Yes, 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 yes. there are currently over 2,800 Apollo asteroids known, Earth-crossing asteroids with A less than 1 astronomical units, but with an aphelion outside the Earth's orbit are called A10 asteroids. There are fewer than 500 A10 asteroids known. Most of the known Apollo and A10 asteroids are tiny. The largest, named Sisyphus, is about 10 kilometers across. However, even a small asteroid can gouge out a big hole if it strikes the Earth. So wouldn't want to be struck by them. However, even at a small, which accounts for the careful way in which astronomers have been cataloging near-Earth asteroids. We kind of do want to know about the near-Earth asteroids because if they do hit us, that would be kind of bad. Oh, thank you, John. I think, John, you asked about whether I like Interstellar. I do. I really like the Interstellar music, actually. So sometimes I like the movie because its music is really good, and Hans Zimmer, really love him. And Interstellar as the topic as well was not bad. I do think that the music makes it or breaks it though. So I loved Interstellar, but pretty much mainly because of its music. Hans Zimmer, yes! Hans Zimmer, isn't he great? Yeah. Honestly, if I think about like that movie's scenes, it's the music that makes it. Like the dun dun, like the how do I even say it? It's the, oh my gosh, I kind of want to play the music now. The Interstellar music. You know what I mean? The like the, it's sort of like the, it's like the music captures the passing of time almost. And it's almost like, I mean, the special relativity showed in, well, actually even general relativity, the relativity shown in the movie was not bad, right? It was not bad. So I feel like the music though kind of captures sort of the passage of time and how that's like relative. No Time for Caution. Yes. Oh, love it. I made up for it in an hour than the wasted 4 years. Oh, Andrew loves music. You should hear her singing. Yes. Who ruined what movie? What do you mean? Maybe we'll listen to a little bit of Interstellar tonight. Hey, don't say anything about Sandra Bullock. I like her. I like Sandra. What do you mean? It's just like, how do I even say, I wish I could sing Interstellar. It's that like coming up and then going down and then the time kind of moving differently through the music, I feel. So anyway, even a small asteroid can gouge out a pretty big hole if it strikes the Earth, which accounts for the careful way in which astronomers have been cataloging near-Earth asteroids. At present, no known asteroids are in an orbit that poses any danger to life on Earth. Typical orbital eccentricities for asteroids lie in the range between 0.05 and 0.3, while typical inclinations are between 0 and 30 degrees. So lots of diversity when it comes to those numbers. The relatively high inclinations of asteroidal orbits result in an asteroid belt that is not a thin disk like Saturn's rings, but is toroidal. You ever hear that my heart will go on meme cover? No. What do you mean? Some asteroids are in orbits that are nearly identical to that of Jupiter, except that they lead or follow Jupiter. Every night in my dreams, I see you. Some asteroids are in orbits that are nearly identical to that of Jupiter, except that they lead or follow Jupiter by 60 degrees. These asteroids are known as the Trojan asteroids. Trojan. The Trojan asteroids reside near 2 of the 5 Lagrangian points in the Sun-Jupiter system. In the 18th century, the mathematician Joseph Lagrange demonstrated that if 2 bodies of dissimilar mass, the Sun and Jupiter, for instance, are on circular orbits about their center of mass, there exist 5 points where the combined gravitational acceleration of the Sun and Jupiter is exactly that required to keep a small test body on a circular orbit co-rotating with the Sun-Jupiter line. Hello, welcome to the live. Can we get 20 likes? Welcome to the live. Can we get 20 likes? Every night in my dreams, I see you. I feel you. That is how I love you. Go on. Okay. Oh, is it wrong? Is it wrong? Can we get 20 likes? It's kind of messed up she thought about Jack and not her husband. Did she have a husband? Wasn't it just a fiance? Near, far, wherever. Reese, excusez-moi. Reese, you're out of control. Oh my gosh, goodness gracious me. Okay, that was a little bit of tidbit on asteroids. Now we will get a little tidbit on comets. Unbelievable. Near, far, wherever you are. I believe that the heart does go on. My stream has not gotten derailed. Which noise? Once more, you open the door. And you're here in my heart, and my heart will go on and on. Is the door wrong? Can we get 20 likes? Alien, can you please like the live? 20 likes, come on! When we observe the asteroid belt, we can directly detect asteroids down to a size limit of 1 kilometer. This is about comets now. We can deduce indirectly that smaller bodies exist in the asteroid belt because of the impact craters they create on larger asteroids. When we observe the Kuiper Belt, because of its much greater distance, we can detect only TNOs larger than d equals 30 kilometers. 30 kilometers. Nevertheless, we have good reason to believe that smaller icy objects exist in trans-Neptunian space. Imagine an icy body around 1 kilometer across in the Kuiper Belt. If we moved such a body toward the inner solar system, then once it was within 4 astronomical units of the sun, its ices would start to sublime. So as we know, when you get closer to the sun, it gets hotter, things will sublime, such as even methane, right? The resulting gases would form a large tenuous atmosphere or comma that would be more easily visible than the tiny ice ball at its center. In fact, we have just described the behavior of a comet. The nucleus of a comet is an icy planetesimal. Remember, we talked about planetesimals when we talked about planet formation period from the nebula that we all come from. But the nucleus of a comet is an icy planetesimal left over from the formation of the solar system. So they're as old as the formation of the solar system. Typical cometary nuclei are between 1 to 10 kilometers across and have a mass of around 10 to 100 billion tons. So quite massive, but you know, cometary nuclei are often described as dirty snowballs. Dirty snowballs. Since they consist of loosely packed ices mixed with rocky material, spacecrafts have been sent to rendezvous with Comet Halley and with Comet Tempel. Both these comets have nuclei that are cratered and irregular in shape. Their densities are quite low, as in 300 kilograms per meter cubed, indicating that the nuclei must be very loosely packed snowballs indeed. The surfaces have low albedos, so not very reflective. The sublimation of ices has left a surface layer that consists of dark, refractory rock. If a cometary nucleus comes within 4 astronomical units of the sun, the sublimation of ices produces a comma that may be as much as 10 to the 5 kilometers in diameter. In addition, the sublimation releases chunks of rock and dust particles that were previously locked inside the ice. So, you know, depending on what's Inside, the sublimation will release those types of things from a comet. The gravitational force of the nucleus on the gas and dust of the comet is small. Thus, material from the comet is easily driven away by non-gravitational forces. Ionized gas is swept away by the charged particles in the solar wind and forms a long, narrow ion tail. So if your gravitational force is not, huge, you're going to be influenced by other things, such as, for example, a solar wind can kind of blow part of you away, basically. Tiny dust particles are pushed away from the comet by the gentler force of radiation pressure from sunlight. So another thing that may happen is radiation pressure from sunlight. Tiny dust particles are pushed away from the comet by the gentler force of radiation pressure from sunlight. The dust grains form a broad, curved dust tail. Thus, comets generally have two tails. Although from some viewing angles they are superimposed and appear as a single tail, in extreme cases a comet's tails can be nearly 1 astronomical units in length. So very long-tailed things. Comets can be divided into two classes based on their orbital parameters. Short period comets are those with a period of less than 200 years and hence a semi-major axis of less than 34 astronomical units. Short period comets have other characteristics in common. Most short period comets have moderate inclination. I is less than 30 degrees, though a few are retrograde. I is greater than 90 degrees. Most short period comets have fairly large eccentricity with an E of around 0.8 is a typical value. At present, there are roughly 200 short period comets known. The most famous short period comet is Comet Halley, Halley's Comet, with a P of 76 years, so pretty short compared to the periods. It is also one of the few retrograde short period comets with an I of 162 degrees. After a few hundred perihelion passes, a comet tends to lose all its ices. So after, going around the sun and coming close to it, enough times, it's sort of lost its ices because of sublimation. Thus, after less than 10 to the 5 years, so less than a million years, a short period comet becomes an inert pile of rubble. An inert pile of rubble. Given this brief time scale, there must exist a repository of cometary nuclei in the cold outer solar system from which the supply of short period comets is replenished. One obvious repository is the Kuiper Belt. This would explain why most of them have relatively small inclinations, which match the relatively small inclination of the majority of Kuiper Belt objects. But how can we explain the short period comets that are on retrograde orbits? To explain the origin of retrograde short period comets, it helps to consider the origin of long period comets. Long period comets are defined as comets with period of more than 200 years, and hence semi-major axis of more than 34 astronomical units. Some long period comets have periods that are very long indeed, with a period of around 3 times 10 to the 7 years, implying a semi-major axis of 100,000 astronomical units. Long period comets have other characteristics in common besides their long orbital periods. These are as follows. Long period comets have random inclinations to the ecliptic, with as many being on retrograde orbits as on prograde orbits. Long period comets have extremely high orbital eccentricities of around 1. Over 800 long period comets have been detected over the course of history. The Dutch astronomer Jan Oort, with O-O-R-T being the name here, proposed that long period comets reside in a large, roughly spherical cloud of radius around 50,000 astronomical units, centered on the sun. This distribution of cometary bodies is called the Oort cloud. The radius of the Oort cloud is not negligibly tiny compared to the distance of around 270,000 astronomical units to the sun's nearest neighboring star. The orbits of cometary bodies in the Oort cloud can be perturbed by passing stars. This alters their orbits and sometimes permits them to approach the inner solar system. Those few objects with perihelion distances of less than 4 astronomical units grow commas and tails and can be observed by us as comets. Retrograde short-period comets, such as Comet Halley, represent long-period comets that have had a close encounter with the Jovian planet that has flung them onto a smaller orbit. So close encounter with the Jovian planet might fling them onto a smaller orbit. The chemical composition of cometary nuclei indicates that they were probably formed about 20 to 30 astronomical units from the Sun between the orbits of Uranus and Neptune, where the temperature of the pre-solar nebula was around 100 kelvins. So remember the temperature on Pluto was around 51 kelvins at aphelion, so that gives you some idea. If they had formed closer to the Sun, they would not have been icy. If they had formed farther away from the Sun, their water would have been locked up in solid hydrates of ammonia and methane. Thank you for liking the live. Thank you for joining the live. Can we please like the live? Can we get 30 likes? Since water vapor is detected in the spectra of comets, so we see water vapor in the spectra of these comets, this clearly did not happen. The orbits of these small cometary bodies were easily altered by encounters with the massive Jovian planets. So they could not have been made in that particular distance, because we see if they had formed farther from the Sun, their water would have been locked up in solid hydrates of ammonia and methane. Since water vapor is detected in the spectra of comets, this clearly did not happen. So the orbits of these small cometary bodies were easily altered by encounters with the massive Jovian planets. If their orbits were not altered, it would be different. Thus, they were scattered onto a wide variety of different orbits. So they may have started somewhere and formed somewhere, but they were scattered about with a variety of ultimate fates. So depending on which comet you are, you may have a different fate. As follows: comets on small orbits made frequent perihelion passages and sublimed early in the history of the solar system. Comets on large orbits constituted the Oort cloud. So they've just become the Oort cloud. Comets on unbound or hyperbolic orbits were able to escape the solar system altogether. So if you wanted to escape the solar system, hopefully you were one of these comets. Those cometary bodies that suffered only minor perturbations to their initial orbit ended up in the Kuiper Belt, a region of relative orbital stability outside the area dominated by the Jovian planets. So that, ladies and gents, was about comets and the variety of comets that we have in the solar system. Thank you so much for joining. Thank you so much for being in the live. Thank you so much for watching this as a video upload later on if you're watching this later on. Thank you so much for liking the live. Please do like the live if you're seeing this. Thank you, thank you, thank you. We just looked at comets. And the chat is talking about Titanic, so feel free to join them or feel free to listen. Thank you. Hello, Siddharth. Let me say hi to the chat real quick. I have to look in this other direction because that's where my laptop is and I can see the chat messages way better than there. Because I'm on my iPad, which is the reason for the graininess of the video, because my phone is broken. See? Oh. Let me clear those. Oh. See? Broken. Hello, Doro. Hello, Reese. Hello, Steven. Hello, Siddharth. How are you doing, Siddharth? And everybody else? We have just been talking about trans-Neptunian objects, including Pluto, Eris, 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 Makemake. What makes a planet a planet? What's the definition of a planet? The dwarf planets. We've talked about the trans-Neptunian objects, and then we talked about asteroids, and then we talked about comets. How is everybody doing? Jack was just another Rose victim. Goodness. Any other astronomy questions? Any physics questions? Nice outfit. Do you think Elon Musk will colonize Mars? Probably. What's your astronomy question, Doro? Oh! I see a question. Why is there far more matter than antimatter in the observable universe? Well, that's a great question. That's a great question. Thank you, Siddharth. Why is there far more matter than the antimatter in the observable? Hello, Wade. Okay, so in short, for your question, Siddharth, we can definitely talk about this in a lot of detail. I love it. Yes, I got your question. Why is there more matter than antimatter? So, simply put, there are more processes that make matter than antimatter. So there are more processes in which antimatter is getting annihilated and turning into something else. Actually, there was a point. Here, let me give you an example. Let me give you an example from my own thesis to answer this question, okay? So in short, there are more processes that make matter. So for example, electron is matter. Positron is antimatter. Positron is the antiparticle of an electron. There are more processes making electrons and keeping electrons than there are making and keeping positrons. So that's why we have more matter than antimatter, okay? Let me give you an example of this. Let me give you an example. Okay, where's my thesis? 1 second. I will give you an example. Yes, right here. Thank you for being in the live. Can you please like the live? I'm just pulling something up here. Thank you, Siddharth. Let me give you an example real quick as well, okay? So the simple answer I already gave you. There's more processes making matter than antimatter, but I have a more specific example for you. So in my thesis, which is called Studies in Particle Astrophysics, which I have actually covered in the channel before, in my lives before, there's a part where I talk about Cherenkov radiation and charge asymmetry. And it's very interesting why we get this charge asymmetry, okay? And it's related to your question. Doro, could you calm down? Yes. Okay. So in my thesis, there is a portion called Ascarian effect. Let me real quick talk about that, and that will give you part of this response. So the Ascarian effect states that ultra high energy neutrinos could be observed through their interaction in a dielectric medium. The principle is that a relativistic ultra high energy neutrino would interact with a nucleus in a dielectric, such as ice, to produce a particle shower traveling in the medium at a speed greater than the speed of light in the medium. So we talked about how Cherenkov radiation is produced by particle showers in the ice, for example, and that's actually related to how we detect neutrinos, or how we try to detect neutrinos. And I talked about this as part of my particle astrophysics experiments talk. So I'm kind of going through it. Fast now. But here's the part about the Ascarian effect, which is basically an example of Cherenkov radiation. So the principle is that a relativistic ultra high energy neutrino would interact with a nucleus in a dielectric to produce a particle shower traveling in the medium, that is the medium of ice, at a speed greater than the speed of light in that medium. So not greater than the speed of light in vacuum, because that's impossible, but in the ice you can. The particle shower would mainly consist of photons, electrons, and positrons. So here's a particle shower which consists of mainly photons, electrons, and positrons. So here we go. Here's an example of antimatter, like you asked about. As it travels through the dielectric, so this particle shower that consists of photons, electrons, and positrons, little particle shower, is going to travel through the ice, through the dielectric. The particle shower develops a 20% negative charge. So we call this a charge asymmetry because electrons and positrons have the opposite charges of each other. So this whole thing could have been neutrally charged, but that's not the case. It is actually negatively charged. And because it's negatively charged, you will see how that's also very important. That's actually why we get the Cherenkov radiation and all that. But anyway, as it travels through the dielectric, the particle shower develops a 20% negative charge. This happens primarily due to Compton scattering of electrons in the medium. So electrons leaving the medium and joining the shower. So basically there's electrons in the medium, I did this motion incorrectly. Here's the shower, here's the medium. Electrons can leave the medium to join the shower. So more electrons from the shower are basically, more electrons from the medium is joining the shower. and secondarily due to annihilation of positrons in the shower with electrons in the medium. So positrons can annihilate with electrons in the medium, and so then positrons are basically leaving the medium. So electrons from the medium can join the shower, giving it more electrons, and positrons from the shower can join the medium by getting annihilated. As this charged particle, so now this is why we get a charged particle shower, which travels through the medium at a speed greater than the speed of light in the medium, and this is why Cherenkov radiation is produced. So this is one example of where in the particle shower initially you had electrons, positrons, and photons, but because of the natural processes like Compton scattering, where electron will leave the medium and join the shower, and because of annihilation of positrons with electrons, positrons basically leave the shower. So there are more processes in nature that make matter and basically annihilate antimatter. So that's the reason why we have more matter. Okay. This is one example of it. In fact, we use the fact that we will get more matter than antimatter in the detection medium or in the detection method for neutrinos in the Antarctic ice through their interaction in the Antarctic ice. In the Antarctic ice through their detection, through their interaction in the Antarctic. What did I just say? In the Antarctic ice through their interaction in the Antarctic ice. Yes. Awesome. Thank you, Siddharth. Thank you so much for coming to the live and asking a question. Really love it. I vote Ondri does some juggling or a backflip or something. You're a good man. She already shook it to Johnny Cash. That's not true. That's not true. Reese, stop spreading misinformation. Ariel. Hi, Ariel. How are you? Hi, Ariel. Peter, how are you? Is there any possibility we could interchange both? I don't think so, but I'm going to think about that question more. Thank you, Siddharth. I don't think so. Peter, how is Australia? Ariel says, I love you. Aw, I love you too. Hi, honey. How are you? How do the planets stay in orbit around the sun? I think someone else asked a question. What's the purpose of Kamioka Observatory in Japan or any neutrino observatory for that matter? I mean, we will be detecting neutrinos all the time, right? So the depends on which neutrino observatory. The different ones are at different energy regimes. So in particle astrophysics, we talked about the different types of particle, or sorry, the different type of, actually, yeah, particle physics or particle astrophysics experiments that can be set up at different energy scales and energy regimes. So some of them are lower energy, some of them are more high energy, some of them are high energy, some of them are ultra high energy. So you want to have a diversity of experimental setups so that you can do experiments at different energy regimes and learn physics at different energy regimes, as well as your sensitivity will be kind of different as well. So some neutrino observatories might be getting neutrinos only from the sun, some of them might be from astrophysical phenomena, some of them could be just leftovers from cosmic ray interaction, all kinds of different things. So by studying neutrinos, so pretty much the simplest answer to your question, whoever asked about that, was I think it was Alien who asked about this. The neutrino experiments, the main thing to note about them is the energy regime in which the experiment is happening, which will tell you different physics and different phenomena. If it's an astrophysical source for the neutrino, depending on which energy regime you're in, you will learn different things. So we have all kinds of neutrino experiments for that purpose. Okay? Because remember, just like we have the Large Hadron Collider, we have the particle accelerators, man-made particle accelerators here on Earth, we actually have natural particle accelerators in the sky. We have some very interesting natural exotic events and phenomena that happen in the sky in extragalactic sources. For example, gamma ray bursts. We took some time on some of the lives to talk about gamma ray bursts, which are actually going to accelerate particles to very high energies. And so if you're interested in collecting neutrinos from sources like that, you'd have to be sensitive to such neutrinos, and your setup has to be different. Whereas if you want neutrinos from the sun, then that's a much lower energy regime that you are probing. Okay, so it's called probing different types of physics at different energy regimes. Okay, thank you for that question. Now let me talk about does universe will stay as long as humans' existence, or will it end at one specific time? That's a great question. It's more like the humans will probably cease to exist and the universe will be there. Steven, are you leaving? So let me give you some timeline. I think it was Siddharth again who asked that question. Let me give you some timeline. So we talked about galaxy mergers on the live recently. So our galaxy, which is a spiral galaxy, will be merging with our neighboring galaxy Andromeda, which is also a spiral galaxy. And this merger will be complete in approximately 6 gigayears. So in another 6 billion years, Andromeda and us will be one. We will be part of the same, an elliptical galaxy. In that timeline, the sun, our sun, will become a red giant. So our sun, if you're talking about human existence, we very much depend on the sun, correct? Well, the sun is still a very young star on the main sequence of stars, on the main sequence life cycle evolution stage of stars. So it's a very young star. It's a very young star. It has gone around the galactic center of our galaxy about 20 times only. So it's a very young star, but in the order of around 6 billion years, it will be a red giant. And so our galaxy will be fine. We will be merged with Andromeda. Everything will be fine in the universe, but we will probably not be here. Of course, we could go to Mars or something as well. I don't know how going to Mars would be much better because it's not that much farther away from the sun. Is this the ring you're talking about? So Siddharth, thank you so much for your question. That prompted me to share this galaxy merger story. So thank you so much, appreciate it. I bought this ring myself from the Caribbean islands. Is it true that quasars are a thing of the past? I mean, they only existed during the early years of expansion. I have one. Do you believe in multiverses? So quasars, quasi-stellar, quasi-stars are active galaxies with an active galactic nucleus in the center. So we have quasars. We found quasars pretty recently. Like, they're not necessarily from the early universe. So if you're asking about the early universe, so it depends on what the meaning of early universe. So in the very early universe, the universe was radiation dominated and there were no galaxies. There were no stars, no galaxies. So, you know, in the very early universe, we can step through the evolution of the universe to sometime. Actually, we already have in some cosmology lives. Yes, we are seeing those quasars as they were in the past. That's true for almost any object that's at a large distance away because light takes time to travel to us. But they're not from the beginning of the universe, if that's what you're asking, because in the very beginning there were no stars, no galaxies, no nothing. It was just a hot soup of cosmic plasma, made up of mainly photons, positrons, and electrons, some neutrinos, and then a little bit of baryons. But yes, quasars are simply active galaxies, so they would still be as, you know, they're as old as, I don't see how they're any older than some other active galaxies. But I could be wrong. Double check the statement. In fact, we can talk about quasars. We can try to find, I don't think I saw anything here about the exact age of quasars. We saw sort of the distances away that they were at. In fact, because they were so far away is how we knew that these things are very luminous. Like, their galactic centers are extremely luminous because they were so far away and they were so point-like. We thought they were stars, but the spectra was not consistent really with stars. So it was a whole thing. We talked about quasars in, so you should go to my live later on just quasars. I think I just call it quasars, and you can listen to it more on everything to do with quasars. But I don't think we talked about their age. That's a good question. I will think about that more, and I'll try to look up more specifics for you. Okay? What's big string theory? Big string theory? Do you mean superstring theory? Actually, I have to use the bathroom. It won't be a very long break though. I have to use the bathroom. Superstring theory? Okay. Let me get your next couple questions in a little bit. Sorry. I have to use the bathroom. For real. I'll be back. It's supposedly before Big Bang? What? What do you mean? Oh, the superstring theory? Okay, 1 second.